Hello everybody, this is Andreas Reinhardt from TU Clausthal, Germany, and today I'm going to present joint work with Christoph Klemenjak from Alpen-Adria University in Klagenfurt, Austria on user activity detection with the help of non-intrusive load monitoring. So let me just quickly walk you through what non-intrusive load monitoring is before we're looking into how to use it for user activity recognition. Essentially, non-intrusive load monitoring, or NILM for short, is a technique that takes in a household's total power consumption, such as the one you can collect from a smart meter, and then disaggregates the contributions of the individual appliances. So you not only get an information of what appliance was running, but also when and what energy consumption was incurred by this operation. You can see that in a sample case on these diagrams on the slide. So on the left-hand side, there's a depiction of the household total, like the aggregate consumption. And on the right-hand side, you'd see it separated by the three appliances that were operative. Use cases for NILM are first and foremost recommendations on how to save energy, because by making it possible to attribute to individual appliances how much energy they consume, and thus how expensive they are to operate, this essentially allows for optimizations once you can tell the people exactly how to cut the costs. And all of that without the need to deploy any additional sensors. So it's device-free in the sense that most people, or virtually everybody, has an electricity meter at home already. So using NILM methods, which are essentially just highly optimized pattern recognition methods to identify where in time where certain appliances operated, allows us to deduce what were the people doing at this time. And so the research question we sought to answer in this paper and in this talk today is, can we use these NILM algorithms to not only detect the operation of electric appliances the way it has used to be done traditionally, but can we also use them to identify composite user activities that involve the operation of multiple appliances? So why do we do that using NILM methods? Well, we had a look at both the related work in terms of activity recognition, but also into the related work on non-intrusive load monitoring. And we found that there was a major uptake and a drastic increase in research activities in the NILM field over these past years. And so many methods have been newly proposed or translated from other domains adapted to the field of electrical signal analysis. And particularly with the rise of applying neural networks to such problems, we've seen very, very good results how to detect the appliance operation from the household aggregate total. So the key limiting factor in state-of-the-art NILM is, simply put, its limitation to disaggregate one appliance at one time instead of permitting for the detection of more complex and composite user activities. And that's exactly why we are proposing NIAD, Non-Intrusive Activity Detection, based on the concepts of NILM, but translated away from recognizing individual appliances and attributing them energy consumption and corresponding cost, towards using NILM to recognize activities and thus infer what the users are currently doing. But the key mode of operation shall remain the same. In other words, we're going to feed our NIAD algorithm the same aggregate consumption data of a household, and we just expect it to not output predictions of what the individual appliances' contributions look like, but rather than that, we just wanted to flag what activity was executed at what time of the day. So in a nutshell, what NIAD is doing is to repurpose existing disaggregation methods, and we're not developing any new ones, existing methods to accomplish a different objective, namely to run a device-free human sensing system based on electrical consumption data. In related work on activity recognition, most of the works we could find in literature are based on a static linking between the operation of certain appliances and the corresponding activities. So for example, if you would observe binary indicators about the operation of a water kettle and a toaster and a stove, then through the means of expert knowledge, that could be annotated as being a breakfast activity. So these static rules are easy to define, but they require a lot of expert knowledge because there might be ambiguous activities that rely on the same appliances, or at least a big subset thereof, but still would be different activities. Now, the question is, how is NIAD different to that static linking? And the answer is straightforward. We want to get rid of the static mapping between the two of them. So we want to just leave it to the disaggregation algorithm to automatically detect what appliances relate to what user activity, and then be able to recognize them and aggregate data irrespective of the order in which appliances are being operated. So sometimes for breakfast you may see different orders in which people start switching on devices, as well as if there's an omission of a certain appliance. So leaving out the bread cutter or a toaster for breakfast doesn't mean that's no longer a breakfast activity. And so all that we need to train NIAD to recognize activities is activity level consumption data and the household total, and we'll just train the disaggregation algorithms to flag certain activity patterns. Now there's one problem, and that's the limitations of real-world data sets. So in fact, there is no real-world data set that has all the activity annotations we need, but none of them that we are aware of have consumption attributed to a certain activity. And also the annotations of when have activities started and when were they completed, that's also something currently available datasets do not provide. And for that reason, we decided to use synthetic data to evaluate NIAD. We used the open source AntGen data generation framework, which can generate individual appliances data, but then aggregate them up to the very top to get the household total. We scheduled a bunch of appliances such that they resembled real-world activities to match up with actual activity cycles. And then through the use of different seed values for the random number generator, we also made sure that no two iterations of the same activity looked exactly the same. But there was always some variance in between, and sometimes that would even lead to the omission of certain appliances from an activity. There's a sample trace shown here in the bottom for 2 days worth of data. That includes a bunch of user activities on top of the typical household base loads like an internet router and a fridge and so on. So using these data that we synthetically generated, we seek to benchmark NIAD and see how well it performs. To this end, we've defined a bunch of activities that will show up in the synthetic data, and those are listed in the table. So there might be the user operating a dishwasher, there might be the fridge autonomously operating in the background. We have an activity to heat a meal just using a microwave oven, to vacuum the apartment, or to start the washing machine. Those activities are different to the ones I'm going to introduce in a second in the regard that they actually just involve a single appliance. So in these cases, NIAD reduces to NILM. We're just looking into the data set and trying to find out, has somebody operated the vacuum cleaner? If so, then that maps to the vacuuming activity. There's a second set of activities that we consider, and those are more composite: watching TV, preparing breakfast, cooking a dinner, or ironing and consuming media at the same time, like listening to the radio or watching a TV show. And for those activities, that's where NIAD is expected to excel. So that's where we wanted to show that we can also detect composite activities for which multiple appliances are required from the household aggregate. We've set the evaluation system up as shown here. So essentially we used the latest version at the time of writing the paper of the NILM framework, an open source tool to run disaggregation on provided input data. And we considered 6 state-of-the-art disaggregation techniques that were provided as part of the framework. For those using neural networks, we trained them for 30 epochs, which is a value that we have empirically determined in numerous other research activities we've done to show sufficiently good results. So by increasing that number, the results won't get too much better or won't improve much more. And for the input data, like I've said, we used the synthetic data generated using AntGen. We scheduled each of the activities I've shown on the previous slide to happen exactly once per day. And those that could run in the background, like starting a washing machine or a dishwasher, they would also run in the background and could be overlaid by users' activities in the front, for instance, a breakfast preparation process. We did create data for 180 days with one sample every 10 seconds and used 80% of that data for training the NILM algorithms and neural networks, and the remaining data to test whether these, how well the disaggregation worked. For the assessment, we used the F1 score. It's just calculated as shown in the equation here, where we've got the true positives, and false negatives, simply translating into if the dishwasher was actually operating and NIAD believed the dishwasher to be operating, then that would be a true positive. But if the dishwasher was turned off, but NIAD still thought it was running, then that would be a false positive. So to make it a fair comparison between those appliances, we got rid of anything that was measured in watts and just used binary indicators about whether an appliance was operating or not. Here are the results for the F1 scores of those activities. The gray ones on the top are those where NIAD reduces to NILM. So we're just looking into how well can we identify those device operations, which happen to coincide with the user activities. The more interesting ones are the 4 activities listed in the bottom, whose results I'm going to detail a bit more on the next slides. So let's look at the activities just to make sure we get a better understanding of what works and what doesn't. So I've just prepared 2 of them for you here. The first one's the breakfast activity. On the left, you see the 5 devices that contribute to that activity, disaggregated individually, from which you can, for example, tell the bread cutter appliance. There's only one disaggregation method, namely sequence to sequence, that can detect its operation at all. But then on the right-hand side, we have the composite activity of having breakfast or preparing breakfast with the corresponding F1 scores along the y-axis. And what we see here is that for some appliances, mainly with the exception of the bread cutter, it's the remaining 4, the sequence to point method actually does a very good job in finding those appliances with F1 scores up to 0.96. But then for the composite breakfast activity, the results are slightly worse than this, and the main reason being that, of course, sometimes there would be devices omitted, sometimes the order of operation would change, and sometimes the operation of the coffee maker and the kettle might be overlapping, so they might be running at the same time, whereas in other instances they might just be separated. But in principle, what we can see here is that the 3 leftmost algorithms, they have a poor performance across the board. So it doesn't really matter much, and we should basically disregard them at this point. But the 3 ones on the right, they do actually show that NIAD achieves almost as good results as the individual appliances NILM. And the same holds for the dinner cooking activity. So again, individual appliance disaggregation results are not really much worse than the results for the composite activity. And in fact, for the S2S, the sequence-to-sequence algorithm, we even see an outperforming result of NIAD in comparison to the 3 individual appliances. Let me summarize this now. So what we've shown is that we can repurpose non-intrusive load monitoring algorithms to not just identify the operation of individual appliances, but rather than that, to recognize composite activities during which appliances may operate or not. Both the sequence-to-sequence and sequence-to-point methods actually succeeded very well in discovering household activities, and the F1 scores of the results were very much similar to the recognition of the appliances contributing to this activity. So in a nutshell, the major advantage of NIAD is we have only a single training phase in which it'll automatically adapt to the typical household routines, to the typical user activities in the geographic area of interest, and then recognize that in household aggregate data without the need for the appliance by appliance training that we usually need in NILM. Well, that's it from my side. Thank you for your attention.